On December 4, 2011, the Iranian military broadcasted a piece of footage that immediately raised alarms in Washington. Sitting in the center of an Iranian gymnasium, resting on a display platform, was an RQ-170 Sentinel. This was a classified military asset. The Sentinel, nicknamed the Beast of Kandahar, was among the most highly classified and advanced unmanned aerial vehicles in the arsenal of the CIA. It was a flying wing, coated in classified radar-absorbent materials, packed with cutting-edge surveillance sensors, and designed to conduct surveillance in heavily defended airspace without being detected. A few days earlier, this exact drone had been flying a covert reconnaissance mission deep inside Iranian airspace, monitoring nuclear facilities. Suddenly, the operators at the control base in Nevada lost contact, and the drone just vanished. The US military assumed the drone had experienced a mechanical failure and crashed into a mountain, and assumed the wreckage was scattered across miles of desert, rendering the classified technology useless to anyone who found it. But the footage on Iranian television suggested otherwise. The RQ-170 sitting in the gymnasium was fully intact, with no bullet holes or shrapnel damage, and no signs of a surface-to-air missile strike. The Iranians had captured the drone without shooting it out of the sky. When intelligence analysts studied the footage and verified its authenticity, a terrifying realization set in. The Iranian cyber warfare unit had not hacked the CIA's command data link. Breaking military-grade encryption in real time is impossible for modern supercomputers. Instead, the hackers ignored the drone's software entirely. Instead, the attack targeted the drone's navigation system rather than its command link. They severed the drone's connections, fed its internal computer a fake set of mathematical coordinates, tricked the drone into believing it's hundreds of miles away in friendly territory, and forced the American drone to land itself perfectly on an Iranian runway. This incident exposed a serious vulnerability in modern technology. The system that guides smart bombs, navigates multi-million-dollar drones, steers massive cargo ships, and synchronizes the global financial grid possesses a fatal flaw. To understand how the Iranians made it happen, we need to look at how GPS actually works, and more importantly, how a system designed to tell an aircraft where it is can be tricked into believing it's somewhere else. To understand how you spoof a navigation system, you first have to understand what the system actually is. When you open a map application on your phone, you see a blue dot representing your exact location on a detailed street grid. This visual creates a massive misconception. People assume that GPS satellites in space are somehow tracking them, looking down at the Earth, calculating coordinates, and beaming a map directly into their device. That is entirely false. GPS satellites do not know you exist. A GPS satellite is nothing more than a very expensive, incredibly precise flying atomic clock. The Global Positioning System consists of a constellation of at least 24 satellites orbiting the Earth at an altitude of 20,200 kilometers. Every single one of these satellites is equipped with multiple atomic clocks, usually rubidium or cesium oscillators, that measure time by tracking the exact microwave resonance of atoms. These clocks are so precise they will not lose or gain a single second in over 1 million years. All these satellites do, 24 hours a day, is broadcast a continuous radio signal toward the Earth on a specific microwave frequency, typically 1575 megahertz. That radio signal contains exactly 2 pieces of information: the exact identity and location of the satellite in orbit, and the exact time the signal was transmitted. That is it, just a timestamp and a location. When a military drone flies through the sky, its onboard receiver listens for these faint radio signals. When the drone's antenna catches a signal from satellite A, the computer reads the timestamp attached to the wave. Let's say the signal left satellite A at exactly 12. The drone's computer checks its own internal clock and registers that the signal arrived at 12 and 0.067 seconds. The radio wave took exactly 0.067 seconds to travel from space to the drone. Because radio waves are electromagnetic radiation, they travel through the vacuum of space at a constant physical limit, the speed of light, denoted as c, which is around 300,000 kilometers per second. To figure out how far away the satellite is, the drone's computer runs a basic algebraic equation. Distance equals the speed of light multiplied by the time delay. By multiplying the 0.067 delay by the speed of light, the drone calculates that it is sitting exactly 20,086 kilometers away from satellite A. But knowing your location from one satellite does not give you your location. It just tells you that you exist somewhere on the surface of an imaginary sphere with a radius of 20,000 kilometers surrounding that satellite. To narrow it down, the drone catches a signal from satellite B, calculates the time delay, and determines it is exactly 21,500 kilometers away from satellite B. The drone draws a second imaginary sphere. When three spheres intersect, they create a massive geometric ring in space. The drone knows it exists somewhere on the edge of that ring. The drone catches a signal from satellite C. The computer draws a third imaginary sphere. When three spheres intersect, they overlap at exactly two distinct points in 3D space. One of those points is usually out in deep space, moving at thousands of miles an hour. The other is near the surface of the Earth. The computer discards the impossible point. Through this geometric process, known as trilateration, the drone isolates its exact latitude, longitude, and altitude. But there is a mechanical problem. To calculate distance using the speed of light, the drone's internal clock has to be perfectly synchronized with the atomic clocks in space. If the drone's cheap internal quartz clock is off by just 1,000th of a second, that microscopic timing error multiplied by the speed of light results in a positional error of 300 kilometers. You cannot put a $1 million atomic clock inside every drone, smartphone, and car on Earth, so the engineers use a mathematical trick. The drone catches a signal from a fourth satellite. By introducing a fourth intersecting sphere into the geometry, the drone's computer has four equations and four unknown variables: x, y, z, and time. The computer uses the fourth satellite signal to mathematically calculate the exact error in its own internal clock, corrects the error, and achieves nanosecond synchronization with the atomic clocks in space. 4 satellites, 4 timestamps. That's the entire foundation of modern global navigation. But dealing with timestamps at the speed of light exposes the system to a much deeper, much more fundamental law of physics. To make this math work, aerospace engineers had to account for the fact that time itself is not constant. In 1905, Albert Einstein published his theory of special relativity, completely shattering classical Newtonian physics. Einstein proved that the speed of light is absolute for all observers, but space and time are relative. If an object moves extremely fast relative to a stationary observer, time physically slows down for the moving object. This phenomenon is known as time dilation. GPS satellites orbit the Earth at incredibly high speeds, roughly 14,000 kilometers per hour. Because they are moving so fast relative to the receivers on the surface of the Earth, special relativity dictates that the atomic clocks on the satellites tick slightly slower than the clocks on the ground. Using the Lorentz factor, physicists calculated that this high-speed orbit causes the satellite clocks to lose exactly 7 microseconds a day compared to clocks on Earth. 10 years later, in 1915, Einstein published his theory of general relativity. This theory proved that gravity is not a traditional pulling force, but rather a warping of the fabric of space-time created by mass. The closer an object is to a massive body like the Earth, the deeper it sits in the gravity well, and the slower time passes. GPS satellites sit 20,200 kilometers away from the surface of the Earth. Up in orbit, the gravitational pull of the planet is only 1/4 as strong as it is on the surface. Because the satellites experience much weaker gravity, general relativity dictates that their atomic clocks tick much faster than clocks on the ground. Physicists calculated that this weak gravity causes the satellite clocks to gain exactly 45 microseconds a day. When you combine the two relativistic effects, the math forces an unyielding conclusion. Special relativity subtracts 7 microseconds, general relativity adds 45. The net result is that time on a GPS satellite runs exactly 38 microseconds faster every single day compared to time on the surface. 38 millionths of a second seems entirely negligible in daily human life, but in the world of electromagnetics, where radio waves travel at 300,000 kilometers per second, 38 microseconds is a catastrophic error. If aerospace engineers ignored Einstein's theories and simply launched the satellites without adjusting the clocks, the 38 microsecond daily drift would completely destroy the navigation grid. In just one day, that microscopic error, multiplied by the speed of light, would result in a positional error of 11.4 kilometers. A military drone trying to drop a payload on a specific building would miss its target by 7 miles. After a week, the error would compound to 80 kilometers. The entire global coordinate grid would dissolve into chaos. To prevent this, engineers physically alter the frequency of the atomic clocks before they launch them into space. They deliberately set the clocks to run slightly slow on Earth, at 10.22 MHz instead of 10.23 MHz, which is rounded up. When the satellite reaches orbit, the effects of relativity speed the clock up, snapping it perfectly into a 10.23 MHz rhythm relative to the ground. This intense, fragile dependence on extreme timing precision is the ultimate vulnerability of the global positioning system. The drone's computer trusts the timestamp on the radio wave implicitly. It has no eyes. It has no physical reference points. It relies entirely on solving the distance equation. If an external force can manipulate that microscopic time delay, they control the drone's reality. And manipulating that signal is terrifyingly easy because the satellites suffer from one major physical weakness. When a GPS satellite transmits its navigation signal from space, it uses a transmitter that pushes roughly 50 watts of power. That is the equivalent power of a standard household light bulb. That radio wave has to travel through 20,000 kilometers of empty space. As the electromagnetic wave travels, it spreads out spherically. The energy of the signal degrades according to the inverse square law. Every time the distance doubles, the power of the signal drops by a factor of 4. By the time that 50-watt radio wave travels 20,000 kilometers and hits the surface of the Earth, its signal strength is measured at roughly negative 160 decibel watts. To put that number into perspective, negative 160 is a fraction of a billionth of a single watt. The GPS signal reaching your phone or a military drone is weaker than the cosmic microwave background radiation left over from the Big Bang. It is an incredibly faint whisper buried under a mountain of atmospheric static. This extreme weakness is what makes the cyber attack possible. In December 2011, when the American RQ-170 Sentinel drone crossed into Iranian airspace, the Iranian Electronic Warfare Unit executed a textbook spoofing attack. The attack happens in 3 distinct physical phases. Phase 1 is denial. The hackers point a directional antenna at the drone and broadcast raw, high-powered white noise on the exact 1.575 GHz GPS frequency. The hacker's transmitter might only push 1 or 2 watts of power, but because the hacker is only a few miles away on a mountaintop, not 20,000 kilometers away in space, their 1-watt signal hits the drone's antenna millions of times harder than the legitimate satellite signal. The drone's receiver is instantly overwhelmed by the screaming static. The signal-to-noise ratio collapses. The drone loses its lock on the real satellites in space. It goes blind. Phase 2 is the capture. This is where the physics of the hijack occurs. The hackers do not instantly tell the drone it is in a different country. If the drone's computer detects that its position jumped 500 miles in 1 second, the internal software will flag the data as physically impossible, reject the GPS input, and switch to its backup inertial navigation system. Instead, the hackers manipulate the physics of time slowly. The hackers gradually, microsecond by microsecond, alter the fake timestamps they're beaming to the drone. By artificially extending the delta t variable in the distance equation, the hackers force the drone's computer to calculate that it is drifting slightly off its intended flight path. The drone's autopilot looks at the fake coordinates. The math tells the drone it is drifting to the right. To correct this supposed error, the drone's autopilot physically banks the aircraft to the left. The drone is now actively flying itself off its real intended course, trying to follow a ghost trajectory painted by the hackers. The hackers continuously shift the fake timestamps, creating a digital breadcrumb trail. They drag the drone's internal coordinate grid miles away from reality. They slowly lower the fake altitude coordinates. The drone's computer believes it is flying too high, so the autopilot commands the engines to throttle back and the elevators to pitch down. The hackers lead the RQ-170 Sentinel drone through the sky, step by step, manipulating the speed of light equation until the drone physically touches down on an Iranian military runway, all while its internal computer firmly believes it is landing safely at its home base in Afghanistan. The Americans lost their most advanced stealth technology because the fundamental laws of electromagnetism dictate that a receiver will always lock on to the strongest signal it hears, and the mathematics of triangulation cannot distinguish between a timestamp arriving from orbit and a timestamp arriving from a radio tower on a hill. The 2011 capture of the Sentinel drone was a wake-up moment in the history of electronic warfare. It proved that manipulating the physical properties of a radio wave is infinitely more effective than trying to crack digital encryption. The physics we've mapped out here are no longer just theoretical exercises used against top-tier military hardware, and the barrier to entry for manipulating the spectrum has collapsed. The hardware required to execute a GPS spoofing attack, which once cost millions of dollars and required state-level engineering, can now be assembled using commercially available software-defined radios and open-source code for less than $1,000. This accessibility has turned GPS spoofing into a global, daily phenomenon, completely reshaping maritime trade, aviation, and geopolitics. We are currently witnessing the rise of massive shadow fleets operating across the globe. Nations and private corporations engaged in smuggling, illegal fishing, or sanction evasion are actively using GPS spoofing to make massive 100,000-ton oil tankers vanish from global tracking networks. Commercial ships are required to transmit their location using the Automatic Identification System, or AIS, which pulls its coordinates directly from the ship's GPS receiver. Smugglers place a small spoofing transmitter on the bridge of their own ship. They broadcast fake timestamps directly into their own antenna. The ship's transponder broadcasts those fake coordinates to the world. A massive oil tanker physically loading illegal crude oil in the Persian Gulf or the Baltic Sea appears on global tracking screens as if it is harmlessly circling off the coast of West Africa. The physics of the hack allows physical cargo to move across the globe completely undetected by law enforcement. In regions of high geopolitical tension, the spoofing attacks have escalated from targeted deception to massive area of effect disruption. Instead of carefully leading a drone off course, military electronic warfare units will blast high-powered spoof signals across hundreds of miles of airspace, broadcasting a single frozen set of fake coordinates to every receiver in the sky. This phenomenon has created bizarre digital artifacts known as circle spoofing. Analysts watching global flight trackers will suddenly see dozens of commercial airliners, cargo planes, and ships appear to instantly teleport to the exact same set of coordinates, usually over an airport or a military base, where their digital icons freeze in a perfect, unnatural circle. For the pilots inside the cockpits of those commercial airliners, the spoofing attack triggers chaos. Modern aircraft rely heavily on the Terrain Awareness and Warning System, or TAWS, which uses GPS to ensure the plane doesn't fly into a mountain. When an airliner flies through a spoofed electromagnetic field, its navigation computer suddenly receives timestamps indicating the plane has teleported inside a mountain range or dropped thousands of feet in altitude. The electromagnetic spectrum has become a highly contested, invisible battlefield. The absolute reliance on the distance equals c times delta t equation has backed the modern technological world into a corner. We built a global infrastructure entirely dependent on hearing whispers from space, making it physically fragile to anyone willing to shout on the ground. To counter this, aerospace engineers and military scientists are desperately trying to sever their reliance on the electromagnetic spectrum. They're returning to the heavy, self-contained mechanics we explored in our previous video on submarine navigation. Militaries are pouring billions of dollars into developing miniaturized ring laser gyroscopes, advanced Schuler-tuned inertial platforms, and quantum cold atom sensors. They're attempting to build aircraft that can navigate by feeling the fundamental constants of gravity and acceleration rather than listening to the fragile transmission of time.